Greetings, building science enthusiasts, and welcome back to the Building Science Podcast. This episode is brought to you by the AIA Austin Committee on the Environment. The committee is committed to providing the architectural and construction community with fellowship and resources that help you deliver healthy, safe, and sustainable environments for people. There's nothing cooler than being dedicated to preserving the Earth's capability of sustaining a shared high quality of life. Check out more at aiaaustin.org.
Welcome to this. Welcome to the
Building Science Podcast.
Welcome to the Building Science Podcast.
Bringing the human factor to architecture and design.
Brought to you by Positive Energy in Austin, Texas.
Okay, hello and welcome back, everybody. Welcome back to the Building Science Podcast. I'm Kristof, here as always with my sidekick, Miguel.
Hey everyone, we're here live at the Hive Conference.
So we're here today to talk about an interesting dimension of the human-technology interface, and what I'm referring to is the house as a technology to promote human health, human well-being. And I'm here with an indoor air quality expert from Lawrence Berkeley National Lab, Dr. Brett Singer. Please say hello.
Hello.
And any more introduction you would like anyone to know about? What's your role at LBNL?
So I am the group leader of the Indoor Environment Group, and I'm also a member of the Residential Building Systems Group, which focuses on energy, kind of the intersection of energy and air quality. And then in indoor environment, we do work in all kinds of buildings, so residences, commercial buildings. Right. We also do a lot of work on pollutant exposure, how pollutants move through the environment, how they wind up in our bodies, sources, etc.
Wow. So you can see why I want to talk to him.
Fun stuff.
So you work with some luminaries or people that I know of, right? Like, is Max Sherman there?
Max Sherman is recently retired, but
really?
I got the pleasure of working with Max for quite a number of years, and he's still bouncing around the community. He does a lot of work with ASHRAE, so he travels and consults, and we still get some of his time here and there. But
good old Max Sherman. And then the Ian Walker.
Ian Walker is work very closely with Ian. He's world-leading building scientist and a pretty good rock musician as well. Yes, and a great colleague, so we work closely.
And then Woody's there, Woody Delp.
Woody Delp is a tremendous research engineer. He's one of the most broadly talented people I know in the business.
That's awesome, you're finding compliments.
He does it's easy. These guys are great. He does simulations, experimental work. He grew up doing HVAC. His dad was an HVAC installer, so he's been doing this his whole life, basically.
Oh, that's
so
awesome.
He brings this tremendous mix of real-world experience, really good mechanical sense, but also understands the theory and really good tools on the analysis. Does great visualizations. I could spend a whole hour talking about what he's telling
That's awesome. All right, let's move it forward. So we just did a seminar together here, a workshop together, and you brought up the Corsi code. Do you think you remember those numbers well enough to go through those, or the ballpark of those? You were referring to the numbers that came out of the National NHAPS. What is that?
National Human Activity Pattern Survey. Look, the numbers are not so critical. The basic idea is that we spend most of our time indoors. I think people know that intuitively. Just think about what you did today or yesterday or the day before. And for most of us, most of that time was spent indoors.
Yeah.
The single place where we spend the most time indoors is, of course, our home. Mm-hmm. Although depending on your job, if you work a lot, your office may compete with that, unfortunately.
Or if you work from home, it's definitely...
Or if you work from home. So it's something like 90% of our time inside enclosed spaces.
Wow.
Some small fraction of that is transportation. As I mentioned today, if you live in LA or a place with a lot of traffic and you have a long commute, you could actually spend 10% of your time commuting in your vehicle, right?
But normally it's like 7%.
It's maybe 5% or something on average across the population, but it varies a lot from person to person. But your home could be 60-70% of your time could be spent inside your home, okay? And it could be even, depending on your situation, even more than that. So that's the environment where you're spending most of your time. Most of the air that you're breathing is inside your home. So even for outdoor air pollutants, the place where you take in more outdoor air pollutants than any other places for a lot of people is in your home. Now again, depending on your situation, it might be while you're commuting or if you're spending a lot of time in the office, but the home is a really important environment for your exposure to potential health relevant contaminants.
So things like ozone, combustion exhaust, you're breathing those outdoor pollutants in your homes.
Yeah, no, ozone's a little bit.
Tell me, what are you breathing?
Ozone's a little bit of a special case because
it reacts on the way in.
Because basically ozone, it reacts on the way in, it reacts with everything, all the surfaces inside your house. So if you have,
you won't breathe it.
Most people
can breathe it.
Most people keep their windows closed. Okay, for a lot of the year.
Interesting.
There are places like Atlanta where I understand people keep their windows closed all year. I asked somebody when they opened their windows, and they looked at me like I was crazy. No, this is somebody with air conditioning. So if you're unfortunate enough to live in Atlanta without air conditioning, then you have bigger problems
Definitely have windows open.
than pollutant exposure. Ozone is a special case because if you have your windows closed and you have reasonably tight house, even a modestly tight house, your ozone concentrations inside your house may only be 5 to 10% of what it is outdoors.
Oh, okay.
Could be even less than that.
So I brought up a wrong one.
So ozone is not. Now particulate matter, the term is PM 2.5.
That's something that's coming up. Let's talk about that. Yeah,
we'll go right into it. So PM, fine particulate matter is particles that are smaller than 2.5 microns in diameter. So if you think of little spheres,
but they're not necessarily spheres.
But they're not spheres. So PM10, that's the model we have. PM10 are particles that we say are quote unquote smaller than a 10 micron diameter. What we really mean is that it behaves like a sphere of 10 microns in diameter. Okay. And then the PM 2.5 is like a sphere. So
it's the aerodynamic.
It could be aerodynamic or it could be optical. In the case of the regulations, it's aerodynamic. But the basic, putting all that aside, the important point is that PM10 is stuff that you can kind of breathe in, right? So it will come into your body and it will deposit in your nasal passages, your upper respiratory. PM 2.5 gets down to the lower respiratory, so that's getting down to your lungs.
Your alveoli?
And then there's another, yes, and get down there. And then there's another category we call PM ultrafine particles, which are particles smaller than 100 nanometers or 0.1 microns. And those are particles that not only get into your deep lungs, they deposit all through your respiratory system, basically, and they can actually move out of your respiratory system. Other particles can too, but they can move through other barriers in your body that the bigger particles can't get through. So even like the blood-brain barrier, some of those ultrafine particles.
Whoa!
So those ultrafine particles, they have some different dynamics inside your body, and also some different dynamics in the environment.
Interesting. So what about the fine particles that can get down into my alveolar region?
Yeah.
What happens there? Do they just sit there inert forever? Do they interact?
They interact. It's not my area of expertise. I can't tell you a lot about that. But basically, it's a foreign substance that's in your body. Now, some of this stuff, wood smoke, right? We've been sitting around campfires for a long time. Okay, in terms of our development as a life form, right? So we're in some ways, our body is in some ways adapted to having those chemicals inside our body because we've been seeing them for a long time. Now, with a lot of things, your body is able to deal with some amount of these things and process and take that exogenous matter and protect against it. And the problem is when we have too much of it for your body to kind of deal with. So if it's sitting around a campfire a couple times a year, I think we're probably most of us are okay. If you have some kind of serious breathing or heart condition, then maybe not. But healthy people, fine. I live in Northern California. We just had about 10 days of really bad wildfire smoke, and the levels that we were breathing in day after day after day were definitely beyond the defensive abilities of most of us. So we're going to see there is people, even healthy people, will be much more vulnerable to respiratory infection. It's an effect that we see when there's really bad air pollution.
Mm-hmm. And you could see the smoke in the air?
Oh, it was apocalyptic. It was Mordor for people who have know that reference from The Hobbit and Lord of the Rings, and they were literally in the mid-afternoon. There was a couple of days where you couldn't see the sun was just a hint of brightness behind this grayness of the air pollution. It was really bad. Anyway, all those particles, they're outside, and they get inside at higher rates than they come in at the same rates, but basically they don't get removed inside as quickly as the ozone. They will deposit on the surfaces of your house, but to a much lesser extent. So I live in Oakland. In a lot of the old homes in the East Bay, and even places like Sacramento and stuff, the older homes were leakier. Those homes, if they weren't running an air filter, people probably had indoor concentrations that were 80% of the outdoor concentrations. Let's say 89. It could even be 90%, depending on how leaky the home is. It's a little lower, but it's not that much lower. Okay, my home is maybe 10 to 12 ACH50 because we've had some air sealing retrofits done, and when we weren't running the air purifier, we had a portable air purifier. It was maybe 70% or something of outdoors. Okay, and then when we ran 60 to 70%, when we ran the air purifier, we bring that down a little bit more. If you take, we did an experiment a few years ago in home in Sacramento. It was a 2006 5 ACH50. Your listeners will know what a 5 ACH50 home is. So this is about a 5 ACH50 home. I think it was 5 ACH50. Maybe it was a little bit more in that ballpark though. And running an exhaust ventilation system at the code required ventilation level, and I don't remember whether it was 2000, which code it was. Okay, but so we're running code required exhaust ventilation. The indoor concentration of PM 2.5 from outdoors was about half of what it was outdoors. Okay, so even not very tight shell, running it at maybe it was about 0.25 to 0.3 ACH operational, right? Mm-hmm. And we were seeing, again, indoor-outdoor was about 50% in that situation. And then if you filter, obviously drive it down. But it gives you some idea of the range. And if it's a tighter home, it's going to be lower. So maybe if it's a 1 ACH or 2 ACH50 home, maybe you drive that down to 30% or 40% or something.
Right. Mm-hmm. But then if it's that tight, then you have the other source of pollutants, which is
then
us and our activity.
Right,
yeah.
Exactly.
So before we leave the particles, particles and gases, you typically hear that the two types of indoor pollutants are particle phase materials and gases. Is that the way you think of it as an IAQ scientist, that there's particles and gases? And could you talk about, I guess what I'm getting at is aerosols and gases turning into particles, that kind of nebulous area between the two.
Yeah, it's interesting. It's certainly one framework to think about. I think more in terms of chemical pollutants and biological pollutants.
Oh, cool.
And what's happening, so let me stay with the chemicals for a minute, because when we talk about particles and gases, you're in that chemical realm, right? And particles are physical things, right? So there's a certain physical first of all, when we talk about the harmfulness of PM 2.5, there have been a lot of studies that try to figure out, okay, what exactly, because the way that we know that PM 2.5 is harmful, the main way, the real strong evidence is that we see outdoors when PM 2.5 levels go up, more people go to the hospital, more people die, more people have various health ailments. Okay, so we have these, we call it epidemiological evidence.
Right.
So there's a tremendous amount of epidemiological evidence, and many researchers have done really good work showing particles go up outdoors, we have health effects. There's some amount of direct human exposure studies, but many fewer, and then there's some occupational studies, things like that. But there's a lot of researchers trying to say, okay, well, can we find specific elements that are when those elements or contributors or basically parts of the PM 2.5, so specific chemicals or specific physical things, so
right.
Metals or organic carbon or carbon, we call it black carbon or elemental carbon, so the more carbonaceous stuff that would come out of diesel trucks, right? So when we see some element of that go up do we see more health effects. And the results broadly from those studies are they're inconclusive. So there are some studies showing that, it's when organic carbon goes up, we see more health effects, or when the black carbon fraction goes up, we see more health effects, or when the metals go up. So every almost acids, right? The organic acid, almost every element. There's been some evidence and some reason to believe that element maybe has a particular biological effect that could account for some or a lot of the effect of the particulate matter. Mostly those studies have been inconclusive. So basically, we say, look, without knowing exactly what's harmful, we're just saying broadly it's good to reduce your exposure to these fine particles. These are, again, these are materials that your body doesn't need, right? We don't need to have those coming into our lungs, so we try to keep concentrations kind of as low as possible. We don't need to live in clean rooms, right? So if you're staying within the federal or California state regulations, so there are federal regulations for what is acceptable levels of particulate matter. I think if you're staying within those levels, you're probably in pretty good shape.
And so, I was talking about particles and gases, and you said, no, you like to think of it actually as chemicals and biological components. So what's the difference there? Why do you make that distinction?
Well, so there's different sources and different, and there's overlap there too. Let me say one more word.
Yeah, so it's not easy for an outsider to get a sense of it.
It's not easy. It's very complicated, and
let's try to make it easy.
Let's try to make it easy. So I think this is something you spoke about at the conference. This is a paradigm that Bill Nazaroff, as a longtime professor.
That's where I got the 5 principles.
At UC Berkeley, and it was
and
one
you
of
worked
my.
with him, or
he was one of my advisors as a graduate student. So I've known Bill for 25 years.
That's awesome.
And
I've credited him, by the way.
Yeah, no, for sure. And I consider him a good friend and really a luminary in the field.
Yeah, absolutely.
And he boils it down and he says, start with a good enclosure. Second thing is to limit what you're putting in. Try, basically not dump a lot of poisons into your environment. So what you release into the environment. So good enclosure, limit emissions, keep it dry. Ventilate and do air cleaning as appropriate. Okay, and it's roughly in that order. The thing he doesn't that you might miss in that is that when he says a good enclosure, there's quite a few things that are implied in that good enclosure, and we were just talking earlier, right? That number one thing by far is keeping your enclosure dry. Right, so when he says keep it dry as number 3, what he means is the air inside the space dry. But keeping the enclosure dry is, at least to me, by far the number 1, because that's what's going to make your house fall down, number 1. Okay?
And these biologics.
And number 2, if you start growing stuff inside your enclosure, it's going to get inside your house. Okay, so keeping it dry is really important. I'm sorry, keep the good enclosure. So it's watertight and airtight. And making sure there's no condensation inside the enclosure, right? Those 3 things. So you have to think a little bit about how air is moving, how where is your cold surface, how much moisture is coming into contact with your cold surface, et cetera, and then potentially drying potential, right? So if we can design it as great as perfectly as we want, but moisture may still get in. And if moisture gets in, it needs a way to get out.
Right.
So robustness comes into it, right? The good enclosure is one that is also robust, which also has some drying potential.
Okay.
That's number 1. And then the emissions, we could talk a lot about that.
Yeah, you don't need to go through the 5 principles. They'll be woven in. But I want to take you back to the gas phase pollutants, the poster child are the VOCs, SVOCs, carbon monoxides, carbon dioxides. Tell me about that. Are those particles?
So this is one of the
gases?
reasons why I say about the particles and gases, because there's a lot of interaction, right? So
right, exactly.
There are chemicals that come into your house as part of the particulate matter,
and then they get heated up.
That they don't even have to get heated up, is because there is a dynamic equilibrium of the chemicals between being condensed, in a liquid form, basically, or sometimes even a solid form, and then what's in the air, and then in gaseous form. So then you bring that particle inside where there's a different mixture of gases, and the
surface chemistry.
The poster child for this is a chemical called ammonium nitrate, where it will outside be in equilibrium with ammonia nitrate in the air, and then you bring it. And I may have to follow it up because I have to check to see. I think it's I remember with nitric acid. I think it's nitric acid, but any case, it's in a dynamic equilibrium outside. You bring it in. The gases actually get removed onto surfaces, and then the compound that's in the particle form will then evaporate, basically, right, or partition into the gas form because there's not as much gas of those gases that are in that dynamic equilibrium. Organic carbon. So there's lots of chemicals, these semi-volatile organic compounds that may come into your house as part of the particulate matter, and then inside your house go back into the gas phase, or actually a lot of times it happens the other way around. You have more organics in your house, more of these semi-volatile organics in the air in your house because you have sources inside.
And you don't just mean phthalates, plasticizers.
All those things. That's included. Okay. So actually, one of the mechanisms for those things to leave your house is actually via these fine particles. So fine particles which are coming through your house, it's coming from outdoors, or maybe generated inside your house, while they're in your house will pick up organics.
Right.
Okay.
This is what I wanted
in very small amounts. Okay, but it'll pick up small amounts of these things and then carry them out of your house when the particles leave your house with ventilation, and that's one.
Or they get stuck in the filter.
Okay,
perhaps.
And the reason why they're being carried out on the particles is because these things really don't like to be in the gas phase. Some of these chemicals, right? They really want to be condensed. So, molecules that make it out into the airspace of your house, okay, are going to look for another surface to condense onto, okay, and that could be a surface of your house.
Absorb onto? Is it?
It's you can think of it as
absorption.
It's absorption. You can think of it as an absorption process because it's a reversible, right?
But we call it condensation too, or is it accurate to say?
That's a good question. I have to
because we call them condensates, but technically, condensation could occur on that glass over there. And I would
condensation
say
is basically whenever you have. We typically think of condensation when you see like a droplet of
water,
the actual chemical itself, right?
Right.
And what we're looking at here is more that there's it's the reason called absorption is because it's not going to be a droplet of that chemical. It's going to be a particle or a droplet that it has other organics in it. So this organic chemical will be have a lower energy state essentially to be part of that droplet, right? Exactly, adhered to that droplet. So because it's
chemistry,
it's happening kind of at the single molecule level rather than at the bulk
cluster of molecule,
at the bulk material level.
Yeah.
So that's why we typically would call it more absorption.
Yeah, good.
Okay, but it's basically the important part is that there's not a lot of it in the gas phase. So when one of these chemicals gets out into the gas phase, it's gonna mostly look to another surface, and that could be just going right back onto the carpet where it came from, or the wall,
right?
Or
but meanwhile,
if a particle's in the vicinity, it might stick to that particle instead, and then once it's on that particle, it's going to stick around there, and then as that particle moves to your house and moves out, it's going to go out with it.
Right.
Okay. So
good.
So that's why when I say the chemicals and gases, yes, there are some things that are entirely in the gas phase, and there are some things that are entirely in the particle phase, and there's a bunch of stuff in between that's going between gas and particle phase.
There you go. And I think that's that last part that I wanted to talk about. And it's not just that, but and I don't want to stay on this too more. We need to get through it, but the idea being that if you're wearing like some cologne and someone's cooking, now you have interactions between those two, and you could have formaldehyde from cabinets or something. So you get all these chemical interactions in the home, right?
Yeah, I'm glad you brought it up, though, because it points to one of the great successes that we've had. So we've had a lot of successes for improving indoor air quality. I've been giving it talks. Yeah, no.
Go Lawrence Berkeley.
No, it's not Lawrence Berkeley. It's a whole community of people. We contribute to that. The talk I gave this summer at summer camp, I really struggle with what to say to people, right? Because there's a lot of people in the crowd who are building homes, who are manufacturing equipment going into these homes, and most of these, there's a full gamut, right? From
Just for a quick second, summer camp is the West Fruit Symposium on Building Science every August.
Thank you very much.
Okay.
Run by Building Science Corporation, they do a great job. They've done, they've contributed a lot too over the years.
Yeah, absolutely.
So, love those guys and women.
You're wondering what to say to that audience.
So I was wondering what to say to this audience, and the show really was, okay, there's a lot more attention about indoor air quality now than there used to be. So there's a tendency to think that things are worse now that we're kind of more aware of them. But actually, things are so much better than they used to be.
That's fascinating.
Right? And I brought up a couple of things. I grew up in a house where my dad smoked all the time in the house.
Me too.
And in the social group we were in, it was rude to ask somebody not to smoke in your house.
Yeah.
Okay? And now thinking, in most places, even in places where people do smoke inside, I think it's pretty common that somebody would at least ask if it's okay, or they wouldn't light up a cigarette in someone else's house unless they knew that was okay with the person.
Oh, absolutely.
And
That's
I put
a
up
good
a
point.
slide today showing that even homes of smokers, right? More than half of the homes of smokers have smoking bans inside the home because smokers have realized that they're willing to take chances with their own health, but they're not willing to risk their family's health, right? So they have, maybe they're hooked, maybe they can't quit, maybe they just enjoy it, and they're willing to, have the all the negative consequences that go along with it. Or
That's a really good perspective.
Okay, but they're like, okay, this is me, but I don't want my kids or my wife or my mother-in-law to have to deal with this, right? So I'm going to do it outside. So smoking,
Generally, things are
smoking is
better.
much better. Volatile organic compounds, right? Everyone thinks, volatile. So formaldehyde, right? Formaldehyde used to be a big problem. We used to have really high formaldehyde levels.
It is a VOC.
And that's one of the VOCs. And we realized the sources from the insulation and other sources, and we manufactured wood products. And through a whole series of things, we've driven down formaldehyde levels. We just did a study in California and found that if you are using the materials, the manufactured wood materials, that are compliant with the California Resources Board regulations, which we assume all of them were because they were homes built after those regulations were in place. And these homes had code-compliant ventilation, which was operating when we made our measurements, which is, again, required in California code. The formaldehyde levels were way lower than what we've seen in new homes in any prior study. Okay. Now, there's still some question about whether they're low enough. Okay, but it's really a big advance. Tremendous reductions in outdoor pollution in most places. There are a few places that are worse than they used to be, but most places are way better than they used to be. So that's a big advantage. It's a big improvement over indoor air quality because so much of our pollutants indoors come from outdoors.
Right.
Volatile organic compounds. Actually, we've reduced VOCs in a lot of consumer products, including some specific ones. Benzene is a carcinogen. We used to actually have benzene in consumer products. We don't anymore because they realized that it's harmful, so they took it out. We greatly reduced benzene in gasoline. Other VOCs that were in consumer products that were harmful, we've taken out. So there's been a lot of advances to reduce our exposure to pollutants. And the bottom line, long-winded lead up, is that most of us are living in homes where the indoor air quality is actually pretty good. Okay, so we're
But could be better?
We're concerned. Yeah, it probably could be better. But I think that most of us are living in homes that I would consider to be basically okay. That we're not. You can always measure chemicals. You can always find things that could be reduced. But the question is, are we living in environments which are substantially risky to our health?
Right.
Okay, and I think for most of us, we're not. Now, there's lots of exceptions to that.
There's at-risk populations.
At-risk populations, and I'd say, the biggest exceptions are houses with sort of active dampness and mold problems.
Yep.
Okay, so those things are, I think, broadly risky to the population, right? So your sensitivity to dampness and mold-related health effects is not, it doesn't align with some of the other things. So you don't need to be an asthmatic or a COPD patient to be sensitive to dampness and mold. Lots of healthy people living in homes with a dampness or mold problem actually develop
respiratory issues,
et cetera, right? So it induces it basically induces conditions.
And there are certain molds that can produce mycotoxins that can be neurologically toxic.
Yeah, and even there, we're still trying to figure out like exactly what it is, right? So what species essentially within these homes are dangerous to us, and we still don't know the answer to that. We don't even have great metrics for figuring out when a home is risky. I say that because almost every home, every home has mold in it, right?
Absolutely.
It's all around us. It's outside. Mold. The term mold, right? So these species that we consider to be mold, fungal species are all around, right? So it's not that fungal species, but we know from experience that if you can see or smell mold in a home,
And mildew is mold.
So if you can see or smell it, right? If it smells musty,
Yeah.
okay, that's mold. And if you see it or smell it, there's a greater chance that somebody in the house is experiencing symptoms.
Yeah.
Now, that doesn't mean that that everybody who enters that house or spends time in that house is going to have negative health effects. It just means there's a greater chance of it, right? So, and then there's another measure, a culturable species that you can take a sample and culture it, and there's some associations there. But these are associations, so they're highly imperfect. So, again, precautionary principle, it's kind of like the particles, right?
So association is worse than a correlation? Sorry, I interrupted you.
Yeah, no. So an association means that we look at a group of people, or often two groups of people. We say, okay, across big groups of people, when we see more of this thing, do we see more health effects?
Yeah.
Right? That's an association.
So it's similar to a correlation.
Okay. And a correlation is there's a dose response. So you're saying, okay, association is the two things go together, okay, and an association and a correlation actually can be the same thing if there's a dose response, right? But the bigger issue is whether it's causative, right? So have we ruled out other things? Because two things might go together, but there might be a third thing that's causing both of those things.
Right.
Okay. So when we get to causative, we usually have two other elements of it, which is we rule out other stuff and we have a mechanism. So with particulate matter, actually, the health scientists have done great job of figuring out exactly how do particles interact with our bodies to cause the effects that we see from these epidemiological studies. So it's rock solid because we say, okay, people get sick, and we have the physical, biological mechanisms whereby the particles in our bodies are causing our bodies to respond in a certain way that lead to the symptoms or the effects that we see.
Right.
Okay,
so I want to just make this clear, and then we'll get into the next topic. That the reason we started talking about all the pollutants is because the pollutant concentrations in the environment, they don't cause health effects, but they lead to the exposure, and they lead to the uptake, and that leads to the dose, which can lead to the response. And we can't really control any of that except for the first part of the chain. Do you agree or disagree?
Oh, I'm sorry, I disagree.
Okay, tell me. You're allowed to disagragree.
It's your podcast.
So you can't control the... I was thinking you control the population.
We control every part of that.
You can't control my physiological response to a particle.
No, yes, we can.
Okay, control my response.
Yes, we can. I think. Now, again, it's not my area of expertise, but in fact, so last week we had a couple weeks ago with this big wildfire smoke. So LBL.
Oh, you're going to call my behavior.
LBL put together LBL put together some recommendations, and there are others that have put together recommendations for what you can do. And one element of our recommendation was attend to general wellness principles. Get enough sleep. Okay, eat well, and hydrate. Those three
reduce
things.
your total load.
Okay, no, to keep your general health as high as possible. So your tolerance, we talked earlier, and I don't know if this will make the podcast, but we talked earlier about how your body has some ability, your body has defenses, right? So we're constantly exposed to pathogens that our body is dealing with, right? So when you get sick, it's not always that you've been exposed. Sometimes you're exposed to something your body hasn't seen before. That's definitely like one way to get sick, right? But a lot of times we get sick, it's stuff that we're exposed to all the time, but we're our defenses are not. It's basically, again, this is not my area of expertise. So this is what I understand from the physicians, that your body gets run down, and then your defenses aren't as strong. So stuff that would on a different day not make you ill makes you ill, right? So when we talk, so that's the general advice is, look, your body is breathing in all these particles and having to fight off all these things. It's spending a lot of energy fighting off that. And it's going to make you more vulnerable to everything else.
Right.
Okay. So if you get enough sleep and you hydrate well and you don't stress your body out, then you'll be better able to deal with that external threat of the particles. So yes, even your personal susceptibility is something you have some control over.
That's true.
And then you mentioned emission. So yes, there's the sources, but we have a lot of control.
I was actually saying pollutant concentration is what we try to control.
We try to control pollutant concentration. Sure.
With exhaust and sources.
Sure. So yes. Yeah.
And I mean it partly from the perspective of my role as a mechanical designer, and I can do some enclosure consulting as well. But as a mechanical designer, keep it dry, ventilate, and filter. The last three of Bill Nazaroff's 5. Those are things that are on my plate, and I can work with that. The reason I'm sitting across the table from you, Brett, is because one of the things I can design are kitchen range hood systems. And I actually can design them, but I'm really constrained by the architecture. The architect has said perhaps it's on an island and it's a downdraft. Please pick the CFM, right? And I put my heel on my hand on my forehead, like, I can. Can I make the hot gas go up and catch it there? And so what I want to do is talk to you about kitchen range hoods, and just very briefly. Cooking is chemistry, so cooking produces things that we want to capture, probably things that you've already mentioned. Could you just kind of synopsize what comes off of cooking generally? Is that possible?
Sure.
It's a big topic.
So the first big dichotomy is between gas and electric. So if you have gas, whether it's propane or natural gas, it's combustion. All the other combustion appliances that we put in our houses, we're careful, very, very careful to vent the combustion products. Now, gas is significantly cleaner than a wood stove or a pellet stove, right? So it's maybe not as bad, but still, our gas furnace, our gas water heater, we make sure we vent those. Now, we're also producing a lot more combustion products from those other appliances, and it's happening when we're not paying attention. So it is more important to vent to correctly vent your furnace or your water heater. So I'm not saying it's not a good idea. Definitely, you want to vent those, but with our cooking burners, we don't directly vent those. We have some kind of hopefully have an exhaust device in our kitchen. Unfortunately, we're still building a lot of houses. Let's stop right here. We're still building houses in this country, lots and lots and lots of houses without any exhaust ventilation in the kitchen, whether it's downdraft or on the ceiling or a range hood or a microwave or anything. Okay, wow. So that's bad. That's dumb. Please, if you're in any way involved in doing that, stop, please, because it's a bad idea. Okay.
There are a lot of decision makers on
this.
Hopefully,
if you're listening to this, and if you're wondering why. Send me an email. I'll send you materials.
Yeah.
Okay. So the gas, and by the way, this idea of venting is for whether you have gas or electric. Okay, which we'll get to. So the gas produces combustion products,
and that's
the electric coils,
monoxide, carbon dioxide.
So carbon monoxide, not as much.
I don't want to take you too deep into this.
But the combustion products include the biggest one probably is nitrogen dioxide because even if it's burning pretty cleanly, you're producing nitrogen oxides. You produce more nitric oxide than nitrogen dioxide. Nitrogen dioxide is a regulated outdoor air pollutant. It's a respiratory irritant. We've done work to show that in cooking dinner in a moderately sized home, you can get nitrogen dioxide levels in your home with gas. Nitrogen dioxide levels in your home that exceed the levels that EPA sets for outdoor standards.
Wow.
Okay, so we know that the quantities you produce from a moderate to substantial amount of cooking are enough to pollute the air inside your home just from the gas part of it. Now, electric coils obviously don't have that, but they will produce what we call ultrafine particles. The gas also produces ultrafine particles, but the electric coils will produce ultrafine particles.
Wow.
And then, but it doesn't produce the nitrogen dioxide or the carbon monoxide or anything. or the water vapor. Gas also produces a lot of water vapor. And then there's the cooking. And basically the type of cooking really matters. So you can produce these fine particles when you're cooking. You can release a lot of other volatile organic compounds, including a chemical called acrolein, which comes from heating oils, a lot of vegetable oils. And you can get to acrolein levels that are potentially irritable to some or a lot of people, and other stuff, polycyclic aromatic hydrocarbons, other chemicals. So you produce this basically chemical soup. There was recently this great thing called Home Chem where they brought really, really fancy analytical instrumentation. They measured all the different chemicals that you produce when you're cooking. It's really quite astounding. So cooking produces this chemical mixture, including things that we kind of know can be harmful if taken into your body in substantial quantities. So I always caution, I'm not telling you not to cook. Please, cooking is a wonderful thing.
Please eat.
We cook in my house with an old gas stove almost every day. We love to eat home-cooked food. I hope you can enjoy it too. So definitely cook. Go ahead and cook with gas if that's your preference. We can talk about
We're going to talk about range.
We can talk about decarbonization too if you want. Okay, so if you're worried about climate change, there are maybe some better options than cooking with gas. But in terms of your health, the key thing really is the venting. So you want to basically remove all of those chemical pollutants at the source and take them out of your house before they mix around your home.
Right.
And it has the added benefit is it takes the odors out too. Now, sometimes you like the odors, right? You like that, smell of home cooked food, but usually
there's enough coming out.
Enough coming out. The range hood doesn't have to be perfect. But having a range hood,
it's not perfect,
right? Having a range hood, so because all those chemicals, the precautionary thing to do without worrying about exactly which chemicals you're producing at exactly which level and exactly when it's going to get to a harmful level in your house is just vent it, and then you don't have to worry about that. You can just focus on picking good recipes and enjoying the food.
So tell me characteristics of a good vent, right? So height above the cooktop. Do you have a recommendation?
Height above the cooktop is a factor, but is maybe not the most important factor. Actually, your geometry and intuition work pretty well here. Okay, and your own senses work pretty well, right? So if you're capturing most of the pollutants, you can tell because the odors won't be as strong, for example, okay? Sometimes you can see the smoke. Basically, though, you say, what are the characteristics of a good range hood? We call it a sump. Basically, there's some kind of a hood. So you start with physical...
Some kind of a bucket,
Some kind of a bucket, a pan, right? There's something where the plume comes up from the stove and is temporarily captured into something, and then from the top of that thing, that into that hood.
That's a funnel, actually.
That hood, right? So the oldest range hoods were actually hoods. You look back at these old Venta hoods, and they were these giant hoods. Or you go to a commercial kitchen, they have these big hoods. So you physically capture, and then you suck out of that volume. Okay, and that's a very effective system. And then what you want is you want to make sure that hood is big enough and covers your cooking. So one of the things we've done in our research is this is pretty obvious, but we quantified and documented it, that if you cook on the back burner, there's lots of range hoods that don't cover both burners. By cooking on the back burner, you get much better removal because it's underneath the hood. And if you cook on the front burner, which is only half underneath the hood, you get much less.
Yeah. Can you put numbers to that? Well, it's impossible to say.
I can put numbers. Actually, I can. We have numbers. So there's lots of range hoods where if you're operating them at, let's say, 200 CFM, 200 cubic feet per minute, and you're cooking on the back burner.
Which by mid-speed.
Okay, a lot of the, if you buy, let's say you spend $200 to $300, $200 to $250, $300 on a range hood, you're going to have probably 3 speeds. The low speed might be 100 or 125 CFM. Maybe a little less than that installed, because a lot of times the installed,
pressure drop.
Let's say you have a good low pressure drop straight,
Path out of the
smooth
building.
duct, right?
And that's another thing. The path out of the building.
Path out of the
should be
building
direct.
makes a lot of difference. But let's say you're, low speed might be anywhere from 75 to 150 CFM. A medium speed might be anywhere from 125 to 200 CFM, and a high speed is something more than 250. Okay, ideally, and that's and
Up
they
to 400.
and those go up as you buy more power, more expensive models with more powerful fans.
That's on my list here. But
Okay, so but if you're at 200 CFM, which you can get with a lot of range, so sometimes that might be a high setting or a medium setting, depending on all the things we talked about. 200 CFM, you're cooking on the back burners. Most range hoods will be in the 80% or more effective. So 80% of what you produce down at the cooktop is going to get removed. Okay, a good range hood will be close to 100%. Okay, even at 200 CFM with it, if you have that big bucket, right? You'll get 95+%. Okay.
Fantastic.
Now you go
Front
to the
burner.
front burner, and there's a really big range. So at 200 CFM, when you have that big bucket, that hood that covers your front burner, you're still getting more than 80% effective. Okay, maybe even 90% effective, because the geometry is
The plume
still
goes up
and
into the sun.
capture is pulled out. But if you have kind of a more standard model that's only covering part of the front burner, okay, you may only be getting 50. Even at 200 CFM, you might be getting 50% effective. And then if you have a microwave, right, you might be down to 40% or 30% effective.
Wow.
And then if you go to a low speed, all
is
those
common.
numbers come way down. Right? So if you're cooking on the front burner with a standard range, it's only covering half the front burner, and you're running it on low speed, you're doing something, but you
than
may
off.
be only removing 20 or 30%
Yeah.
on that first pass. And then after that, it's just ventilation, right? It goes, mixes around the kitchen, most homes now are open floor plan, so it's mixing all around the house. And then you're trying to, ventilate your house to clean your air as opposed to removing the source.
Okay, so you were elusive on the height above the range, but like if your architects might want to know, or homeowners, we typically say 24 to 36 inches above the range is a good number.
Sure.
You said you can go higher. If you go higher, it should be wider. Right?
Higher should be wider, right? So, you mentioned an island.
Right.
It depends on how much money you have, right? So if you've got an island cooktop and you can afford to spend the $2,000 for those really big, beautiful hoods, which are architectural features, right? They work really well.
Yeah.
Okay. You run a few hundred CFM out of those things, and because there's a big physical capture volume, right, that's over your hood, the plume goes up, gets caught in there, and you don't need a tremendous amount of flow, because once it's in there, you're just sucking out of this basically enclosed
It's got
volume.
a buffer.
It's a buffer,
And
right?
side panels could help, or if it's on an outside wall.
Sure, side panels
low.
can help with,
But not really?
A good friend and colleague, Tom Phillips, he loves the side panels, and they can help.
Or even just cabinets on the side.
So
of
the cabinets on the side, let's say more production homes, right? Cabinets on the side do help, right? Because it helps keep it enclosed. It helps direct the plume, especially if you're cooking on the back burner, right? Because those side cabinets, they're not coming out all the way to where the front burners are.
Right.
They're only coming out to where the back burners are. So if you cook on the back burner, and so you mentioned the height, right? So having it a little lower is generally better, okay? But if it's a little lower, then it might be a little less convenient to cook on the back burners, right? So there's a trade-off there. There's kind of a standard height, right? So if it's a production home and they're putting the cabinets in and it's on the wall, they're kind of made. There's a height and a lot of.
It's like a 12-inch cabinet with a range, and then
It's
30-inch
designed to be something like 30 inches or something above the cooktop. I think is a fairly common number. So your microwave's going to come down. I think there may be 12 to 18 inches or something, depending on the size of the microwave. There's some different sizes there, right? Yeah. So that's going to come down, and that might microwave may only be 18 inches above the cooktop. Because you need to reach it, right? You need to be able to get in there, and you can't rely on being 7 feet tall, right? So for people of common height to reach up and get into that microwave, it has to be lowered down. Now, that's fine if you cook on the back burners, right? Because the microwave's over the back burners. it doesn't work so well if you cook on the front burner. So if you really want that microwave above the range, fine, go ahead. Get that.
Back burners.
Hopefully, those microwave manufacturers will make. There are exhaust units that move enough air.
That's and the sound from microwaves.
But a lot of them are louder because it's a more circuitous route. Okay,
Yeah.
but from an air quality perspective, it works fine.
Yeah.
If they're operated, and you probably need to operate those on a medium or high setting because in the low setting they just don't move they don't move enough air to really be effective. So, cook in the back burner. Turn it on to medium to high, and you on their microwave, and you should be okay. Again, the range hood, if you want to, you talk about the height. So if you're getting to pick the height, then you're probably talking about a home that's a custom home rather than a production home.
Yes.
Right. And then you have a little more flexibility. You probably have a little more ability to pay for more expensive products, so you can, because the products with the big hoods are more expensive, right? So I want to be sensitive for the production homes. You don't need to spend $400 or $500 to get a good range hood. You could spend $200 and get one that has a very quiet low speed setting, has a reasonably has a good tolerable medium speed setting, and then having that high speed setting, even if it's noisy, is really helpful, just in case you burn something or you're cooking a lot, you're using all 4 burners or something. You want to have a setting where you can move 300 CFM because for those few times that you need it, right?
Wait. So we got to go here then. So you said 300 CFM as though it's crazy high, right? We get clients with 1,500 CFM range hoods, right? So it's as though the food will taste 3 times as good if the vent hood goes 3 times as high or something.
No, it just looks better, man.
Yeah, I guess so. Well, why don't they make ones that look like that move 400 CFM?
Well, I think because they're very often, look, if you're going into a high-end kitchen, right, then you're probably having a range
36-inch Viking.
Well, it could be even if it's a 30-inch. Okay, if it's a high-power burner, then you're actually producing more pollutants both from the burner and potentially from the cooking because you're doing higher heat cooking.
That's another
right?
good thing about it. You can control emissions with a heat.
Okay, so higher heat,
lower heat cooking is better,
right?
Yeah.
Might give you more, and
you can control with lids. Actually, excuse me for interrupting.
Sure,
just put a lid on your frying pan.
Sure, but I'm not. Look, I'm an air quality guy. Like, I'm not a cooking expert.
Be the cooking police, Brett. Please, be the cooking police.
I do not want to be the. I want you to cook. I want you to cook however you want to cook. I just want you to have a piece of equipment in your house that can allow you to cook however you want to cook, without polluting your air.
Well
right?
said.
So, and I know that sometimes to do some of those stir fries and stuff, it's less convenient to do in the back, right? There's a reason people use the front burners because it's more convenient. So if you're going to be doing a lot of like front burner, high heat cooking, maybe you're doing, again, a lot of Asian cooking, right?
Yeah.
So, and it's not just Asians who do Asian cooking, right? So it's, I live in Berkeley, everybody's doing stir fries and woks. And that's a higher heat, and it's going to produce more pollutants. It's going to all come in a big slug. The plumes are going to be moving faster, essentially, right? So you have like less time to capture them. It's harder to direct them. So in those situations,
hotter plumes moving faster.
Really, right? So you really need to have coverage, right? But again, whenever possible, like try to get in the habit of turn the range on before you start. Set the setting as appropriate to the cooking you're doing. Cook on the back burner whenever you can, and if you're really committed to cooking on the front burner, then you really need to commit yourself also to having a range hood that covers that front burner. So
does it need to be wider than, like, if you have a 30-inch range? Would you recommend a 42-inch hood? I mean, that's hard to ask for, but.
Sure, it's better.
Yeah.
It's better.
It's better, but
okay, so you're building your custom kitchen. Maybe you do that, but I don't think it's necessary.
Okay, good. One more topic on range hoods.
And by the way, I don't think the 1500 CFM is ever necessary, right? So I mentioned the bigger burners you need more, okay? But let's say you have a 6-burner Wolf stove with the 20+ thousand BTU per hour burners. And you're going to be cooking 2 or 3 things at a time, right? Usually people are not cooking more than 2 or 3 things at a time because how many hands do you have?
Unless it's a team of cooks.
Exactly, right. Okay, so in that situation, you're going to want to have a bigger hood. You want to have a higher airflow, okay? But still, probably 400. I don't think you. I think you really need to go beyond that. If you have a good hood,
Good geometry. Yeah.
good geometry, you really need to go to the really high flows.
I agree.
And the higher the flows you go to,
The more
your
makeup
systems
it.
get really expensive, right? So one of my favorite calls I ever got was a guy, I think it was North Carolina. Maybe he's listening to this podcast, and he and he said, I have an ethical dilemma. So I'm doing this work for this family, putting in their kitchen, and they got the really nice Wolf stove, and then of course they need the big range hood. So I got the big range hood, and then of course that means now I need to put a makeup air system in, and this is getting really expensive now, right?
Yeah.
I mean, they already laid out the money for the stove, and now they laid out the thousands of dollars for their fancy range hood, and now I'm telling them it's going to be another, whatever the amount was for the makeup air system, right?
It's expensive. Good
And
makeup air.
my ethical dilemma is this: I don't think they're ever going to use it. I think it's just all their neighbors and friends have these really fancy systems, and I don't think they're going to cook more than a few times a year. So do I really need to put the makeup air system in? And I was like, yes, you do. You tell them the indoor air quality guy from Berkeley said you do because maybe they're not cooking, but you're building rebuilding a house in this case. I think it was rebuilding. That the next person in may cook a lot.
Yeah.
Right. So they need to have. The system that you're in, it is a
it's
system. The
capable
house
of
is a
that many
system.
pollutants.
You're creating something where if you're putting
Yeah.
in a piece of equipment that's going to move 600 CFM, you need to actually have a makeup air system because it was a fairly tight house. It's a good house, but.
It's fascinating. We think of ourselves as rational. I love this comment you just made about the neighbors. What are the neighbors going to... But we're really very relational, right? So if your neighbors all have, high-power range hoods, you're going to want one.
Yeah.
Even though it might not be needed.
Range hoods are cool. All the cool people have them.
Taste
know
makers, right
Did you
here.
hear that? If you want to own a Tesla, it starts by getting a range hood.
That's right. That's right. I don't even know if they let you drop the down payment for the Tesla
unless you have
without
a
knowing you
range
have a range hood. I just
Okay.
made that up. It's not a real thing.
So speaking of downdraft range hoods.
Oh, downdraft, yeah.
So any comments on that? His
They're not
facial
as good-
expression is a comment. I wish
They're not
you
as
could have seen
good.
it.
They're not as good. Again, geometry. It works out the geometry.
Are they at all good?
Sure.
I guess they're better than nothing.
So if you have gas, then
I don't want to be a leading question asker, actually. So what do you think of downdraft?
lead. I'm able to deal with your. You won't push me around. Don't worry. So we've done limited amount of work with them. So I can. Some of this is intuition, and some of this is data.
Mm-hmm.
We found that when you had there's different. First of all, there's different technologies for downdraft, right? So there's some where it's like just in the middle, for example, of a 4 burner setup, and there'll be like a grate in the middle, and then it sucks down from there, so that it's kind of equidistant from the two sides. Okay. Sometimes it'll be along the back, so it's only close to 2 of the burners, but farther from the other 2 burners, and sometimes it'll be a little pop-up thing. Right?
On the back, usually.
Usually on the back. The back will pop up. So you're actually sucking from maybe 5 or 6 or 8 inches above where the burners are. Okay. So anything where it's adjacent to the burners, you're going to pull in more of the combustion products than if it's somewhere else. Right?
But not more than if it were above the burners.
So you have a downdraft in the back. You use your front burners, it's going to do almost nothing for the combustion products.
Right.
In terms of what you're cooking, we haven't done that test, so I can't tell you. Okay, but usually the release point for what you're cooking is much higher, so it's going to be worse, right? So,
Yeah, exactly.
And again, it's the geometry, right? You got this hot plume coming up,
Yeah.
and you're trying to bend that thing down into the surface. That doesn't work so well.
Not without a lot of volume, which is noisy.
It's what it is. It is, again, helpful for the burners adjacent. If it's working really well for the burners adjacent, you're gonna affect the burners, right? You're gonna see the burners
Suck the flame off.
Yeah, basically, right. So you have to be careful about that. So it's not great, but it's the way to think about it is what it is it's ventilation. It's actually not. It's not equivalent to a range hood.
It's ventilation.
It's more equivalent. It's more equivalent to putting a ventilation fan anywhere else in your kitchen. And actually, if I had to choose, Okay, so it does depend somewhat on the floor plan. Okay, but if we don't build really enclosed kitchens anymore. Okay.
Right.
So that's like, it's almost silly to bother to say this. But if you had an enclosed kitchen, no doubt the fan would be way better on the ceiling than on the cooktop, essentially, right? Because the hot gases are going to go up. You pull them out of the ceiling. Even in an open kitchen. Now, if it's like a really high, if it's a 10 or 12 foot ceiling, then maybe not. But if you have, let's say, an 8 or a 9 foot ceiling, okay, I would still say that. Now, if it's gas and it's adjacent and it's popping up, you're better off with the downdraft. Okay, so a pop-up downdraft.
Better off than
putting it in the ceiling, because if you can put it in the ceiling too, right? And when you put it in the ceiling, then the plume goes up, and the plume's going to be spreading around. But then you're going to be sucking from a place that's, if you put it in something just above, right? I haven't done the computational fluid dynamics to figure out just how.
So you're saying you miss so much of the plume that you. But
what I'm saying is you may be better off putting that 400 CFM, because usually the downdrafts are higher airflow, right? So if you were putting 400 CFM on the ceiling versus on the cooktop, for the cooking pollutants, you may be better off putting it up there than down here. Okay, because at least the plume is going in that direction, and then you're trying to like pull in from the plume. So I don't know what the capture efficiency is there. It's going to be low, but for what you're cooking on the downdraft, again, if it's just on the surface, it's not a pop up, but just on the surface. I don't think your effectiveness is going to be very high for what you're cooking. If it's a pop up and you're cooking right next to it, then probably a little better, and you can probably see it a little bit too, right? So like,
so that means pop up and you're using the back burner.
Pop up and you're using the burner that's next to the pop up. Again, probably way better than nothing, and it is still ventilation. So go ahead and use it. And but if you can put a range hood, it's much better to put an actual hood above it.
So that was a very nicely politically correct way of saying that downdraft isn't as good, but you said it in a nuanced way. Generally speaking, avoid downdraft, but it can be as effective on the back burner if you're cooking near it.
I wouldn't say it's as effective, but it can be substantially helpful.
Yeah, and I guess all this goes to, all this is still better than nothing, which is still happening. All right, so we're going to move beyond cooking now. I just wanted to capture a couple more ideas that came up while you're talking. One is the grease traps, those screens that are in the range hoods. Those should get cleaned. You can clean them in the dishwasher.
I don't think you ever need to clean those things. Yeah, clean the grease screens.
Exactly. And using lids actually is a big benefit right there. Sure. I want to talk about air purifiers and indoor air quality monitors.
Oh, yeah, my favorite.
I want to go relatively quickly. And then we got to talk about your survey. Are portable room air cleaners effective at improving indoor air quality in the room that they're in?
Many are. And the only brands, I won't name a brand, but I'll name an organization. So the Association for Home Appliance Manufacturers, AHAM. And I think, are they an org, or I think they're com, so aham.com. Figure it out.
I think it's an org.
We'll put it in the show notes.
Okay, great. So if you go to their website, they have certified clean air delivery rates.
There you go, CADR. Okay? That was on my list.
So the clean air delivery rates are CADR, and then they have some guidance. I think they say your CADR should be whatever it is, 2/3 of your square feet of your room. Okay, so follow their guidance, and if you pick a product that they've verified that they certify has a clean air delivery rate, and you follow the guidance and sizing, you should be good.
Good.
So that's the simplest I'll say. There's lots of brands and models that work. They have different sizes. The only other thing I'll say is actually what differentiates is sort of filter capacity, cost, noise level, and energy. So I would always recommend for people, there's plenty of Energy Star rated products out there. Okay, I won't mention the model and brand, but I recently went to Costco and bought the one that they had on their shelf, which was $130, and it came with a couple replacement filters, and was an Energy Star model, and it's good for rooms up to, 350 square feet or something, ballpark.
But they sold a lot of those during the fires.
Well, they actually, Costco is a good company in a lot of ways, but they moved product actually to the areas that were most affected by the fire. So we didn't even, they took them off the shelves at my local Costco, and we were pretty badly affected, but we weren't the worst. So they moved them around to get them to the places where they were needed most, which I thought was pretty cool.
Wow.
And maybe other companies did that too, so I don't want to, in any way impugn other companies. But okay, so you can get models for $150. You can buy $150, $180. You can buy a model that will clean a pretty big room. Right, 350 square feet is a pretty big room. Maybe it's 360, whatever, but pretty big room. And often those sizing functions are kind of at the highest speed. The highest speed is maybe a little noisier than what you want. So what I recommend is getting something. You can downsize a little bit. So a lot of times they'll tell you what the CADR is on each setting. Right. So ideally, you get one that provides enough clean air at a medium setting, so you can run it much quieter and not be annoyed by it. And then but the other thing is to pay attention to how noisy they are, because if they're too noisy, you're not going to use it, or you're going to use it at a lower speed.
Same thing is true for range hoods.
Same thing is true for range hoods. And the other place where they're different, these portable air purifiers, is the cost of the replacement filters and how often you need to replace them. So, for example, IQ Air makes really great products. They're very expensive, high-end products. They work really well, and their filters are much more expensive, but you need to change them much less often, right? So you got to pay. And I'm not saying that it's a better deal than somebody else. I'm just saying pay attention to that. Both what the cost is for the replacement filters. Sometimes the unit will be less expensive, but the filters will be more expensive.
Yeah.
Right. And so how often you need to change them? How much they cost? How easy they are to get? Right. Can you just get them on Amazon, or will the company ship them out to you, whatever it is? So ideally pay attention to those features, but start with the AHAB clean air delivery rates and size them appropriately for the room, and they only work if you actually turn them on.
Very good. And just to touch on the CADR, I mean, basically a lot of these manufacturers will say, oh, we do HEPA quality filtration, but you find out it's only at 50 CFM on low speed. So you're getting very clean air, but you're getting a very small amount of it. So
with all the filtration products, this is the filter for your home furnace, your home AC system, your forced air system, the portable, the standalone portable air purifiers, all the marketing of best for allergens, best for this, best for that. I would say you can almost ignore all that stuff. That's all marketing. So for the portable ones, just look at the clean air delivery rate for tobacco smoke. Right? They offer there's some different they do pollen. They do pollen, whatever else. But if it's and actually if pollen is your interest, if allergies is your interest, then pay attention to that one. But for what we think of as air pollution, so particulate matter from outside, certainly the wildfire smoke, look at the one for tobacco smoke because that's the relevant one. And then for your home filters, right, so your filters for your home forced air system or your ERV, there's a couple different ratings. There's the MERV ratings. Your listeners will all be familiar with these. There's Honeywell has FPR. Those are the ones you get at Home Depot, and the 3M Filtrete has I think it's an MPR. Okay, and there's some rough translations, and if you get up to the FPR 9 or 10 or the MPR, I think it's above 2,000.
Right, and love it. They switch all the numbers.
And MERV, it's 12 or 13 or above is where you're getting a really good level of filtration. You don't need to go to HEPA. In fact, HEPA filter systems often have higher pressure drop, and sometimes they're installed as bypass systems, so you're actually not getting a lot of flow. So you want something that's low pressure drop, so you get good flow through it. Usually, they work much better if you're building a new home. See if you can get your builder to set it up, or your builder or mechanical contractor set it up to hold a 4-inch filter is really the best.
Absolutely. Okay.
4 or 5 inch deep. You can get them online. They're a little more expensive, but they last a lot longer. So, and they're much more robust in terms of pressure drop. And if not that, then even a 2-inch filter. So the California Air Resources Board was really interested in getting better filtration in California homes. They work with the California Energy Commission for the new Title 24 standards, and the requirement now is for a 2-inch filter slot in new homes, and they're supposed to have a MERV 13 filter installed at the start. Now people are going to change that, but the idea of the 2-inch filter slot is that it's much easier to get low pressure drop with 2-inch than it is with 1-inch.
Absolutely,
right.
And
so that's a
again
big
with 4-inch.
advantage, and it doesn't mean from manufacturing
you can still screw it up.
You can still screw it up, but 4-inch is better. The problem with 4-inch, of course, is that it won't fit in a lot of places where you have the return. If you have a filter at the return grill, right? There's often not 4 inches there.
Yeah. But you can get 2-inch MERV 16.
But you can always get 2-inch, and MERV 16 is better. But again, I think MERV 13 is fine.
You need to manage the pressure drop.
You get pretty high removal from MERV 13, and you get it's kind of like the clean air delivery rate. It's a function of how much removal you're getting with each pass, and then how much air you're moving through it, right? So with the MERV 13, you can reliably know you're going to get more air moving through it. You don't have to worry as much with the pressure drop, and then you get a high effectiveness. Basically.
Yeah, it's so much to talk about. I guess we should just get close to wrapping up here. But okay, we're going to move on to the air quality monitors. But I wanted to just comment that there are, when it comes to marketing, there are a lot of products with like plasma emissions and ozone emissions and super oxygenated, and you weren't talking about those. You were talking about, maybe some activated carbon or alumina, and then good capture for particles, right?
Yeah. So glad you asked about the ozone and plasma emissions. The first thing I'd say is be careful with ozone. You do not want to buy a product that generates ozone. The California Air Resources Board has done a lot of work on this. They set regulations in California.
Interesting.
In California, it's illegal to buy a unit that produces any substantial amount of ozone.
Whoa.
Okay, so look and make sure that the unit you're buying do not buy an ozone producer. Think of it as a pollutant producer. Do not buy something that produces ozone, period. The plasma is a little different. So plasma or ion generation. So there's two ways that happens. The idea there is that by generating ions, you will charge particles. And we talked earlier about how particles will actually deposit on the materials in your house. Okay, and the more charged those particles are, the more quickly they deposit. Right. So if you can effectively charge particles, you can actually increase the rate that they're removed inside your house. Now, there's a potential downside to this, which is those charged particles, if you breathe them in, they may be more harmful to you. Okay? So, and I'm not an expert to know, and we haven't done the analysis to know, like, what's the cost benefit there, right? Like the cost, the risk, increased risk of breathing in these charged particles versus the benefit of having taken. But I wouldn't, in general, our advice to people is don't try to do chemistry in the air in your house.
Right.
Okay, so there's another technology called photocatalytic oxidation for removing VOCs, right? Where again, you're trying to like oxidize the VOCs to be carbon dioxide, which works great if it all works properly. Okay, that you take these organic compounds and you turn them into CO2. The problem is if anything goes wrong where that reaction doesn't go all the way through, then you're left with these oxygenated organics that are more harmful for you than the chemicals that you started with. Okay, so we said don't experiment with that in your home. Leave that for the chemists to play around in their labs. So the plasma, though, there's another way where they do it, where they will actually try to charge the particles before the filter, right? And if you do that, then particles are removed more effectively in the filter. Okay, so if you can figure this out, if the device is charging the particles before the filter, I'd say go ahead and do it. If it's charging the particles, if it's just pushing charges out into the air, you don't want that. Now those devices that just push charges out into the air are not going to have high clean air delivery rates, whatever. So I think if you stick with the clean air delivery rate, you're probably in pretty good shape.
Okay, good. I'm glad I asked.
Yeah. Okay. That's the.
All right. Last topic then. Thank you so much, Brett, and thanks for bearing with us. This is a long interview. There's a lot of indoor air quality, residential grade indoor air quality monitors available. just leave it at that. What are your thoughts about those? And
Oh, geez. So, okay, so...
I know you've tested some.
So we did. If you go to LBL's website, there's a link
do a
there,
link to that.
And the paper is published in Indoor Air, and it will be available to everybody soon. Right now, it's probably still limited distribution, but you can see the highlights. Though the short of it is that there are now low-cost sensors for some pollutants of interest, and people are packaging these sensors into devices that will transmit the data to the web, essentially, through your home Wi-Fi, and then make the data available to you to see on some kind of app or smartphone app or on the internet.
Exactly.
Okay.
Computer.
Some of these devices will have readouts on the device. Some of these devices will save the data, so you can go back and look at it later. Some of these devices will some of these companies will allow you to download data from their web servers with some limited resolution. So there's all these things out there.
Yeah.
Now the question is, what can you measure? What sensors are available for you to gain useful information? Because if it's not accurate and reliable, then it could be misinformation as much as information. So one of the examples of a pollutant that, quote unquote pollutant, or let's say one of the examples of something that is reported through these devices that is not informative is something called CO2 equivalence. And I won't mention the names of the devices that are doing this, but they have a sensor that's not actually measuring CO2, it's measuring something else, and then it is
to derive
through some association that they've derived, saying what they think the CO2, how that is equivalent to a CO2 level. CO2 is something we exhale. CO2 is really helpful as an indicator of good ventilation. Okay,
Right.
so our building ventilation standards, like in commercial buildings, are designed to keep CO2 levels below about 1,000 or 1,100 ppm. Okay,
Right.
So you can use those ballpark numbers in your house as well. If you're keeping below there, you're in pretty good shape. If you're getting above there, you maybe want to ventilate a little bit more. So having a device that has a CO2 sensor in it that's accurate is really helpful. There are a couple of devices that do, not all of them, but it has to be a true CO2 sensor. The big one, though, is particulate matter, PM2.5. So there's a lot of devices now. There are good PM2.5 sensors that these companies can buy at bulk for, let's say, $25 a sensor.
Wow. Okay,
maybe even a little cheaper than that, depending on what the bulk is. But let's say $20 to $30 a sensor. Okay, so then they're packaging these things into these devices, and they're not precise, but they're accurate in the sense that for a lot of sources of particulate matter, they can give you a number that's, let's say, within a factor of 2. Okay, so it's helpful to but it's helpful to
it's better than nothing. Better than no feedback.
You do a blower door test, okay, and how accurate is your blower door test?
To normal conditions.
Okay, how accurate is your duct sealing test? Right. Okay, great. Point. Okay, so
or even airflow measurements.
Okay, airflow measurements, right? So some of those are better than a factor of 2, but still, getting in the right ballpark is really helpful. Okay,
yeah,
so these get you in the right ballpark, and they can also help you see if what you're doing is effective. So I mentioned this wildfire smoke. Well, a lot of people were doing things. We were telling people things that they could do that may or may not be effective. So you live in an old house. You have a forced air furnace. We're saying, okay, put a better filter in your forced air furnace and run it in fan-only mode. But beware, your ducts may be so leaky that by running your furnace, your forced air furnace, you're bringing in more outdoor air to detriment than you are filtering to benefit.
Yeah.
Okay? Now, if you have one of these monitors, then you could see, I turn on my forced air furnace, are particle levels in my house going down or up?
Yeah.
Okay, great. I have an indicator this is doing something or not doing something. And if you have the same one of those inside and outside of your house, then you can see, okay, how well am I doing? We started out talking about inside-outside ratios, right? So you can see that. So I'd say there are good devices that cost under $300 for particulate matter, and depends on what your application is. So there's a one, I'll mention a few names because these are ones that we've tested that have worked well. I'm not endorsing these products, but there's a couple that I can tell you I know work reasonably well. There's a company called Purple Air. They make their base model is actually for outdoors, and it comes in. They build it into a PVC cap, which is kind of cool, and it's made for, outdoor power supply, etc. And they have a nice map on their website where you can see air quality around, and they have some conversion factors. So that's a good device for outdoors. They make an indoor model too now. So that's a good thing where you could buy one for indoors and one for outdoors and see, using the same sensor, what the comparison indoor and outdoor is. Another one that we tested is a company called Air Visual. It's owned by IQ Air, but Air Visual Pro is the model now. That one has it's really, you can put it outdoors, but it's not built for rain protection, so you need to put it under something. So if you can put it in a rain protected outdoor space, they work fine outdoors. That measures particulate matter and CO2. Now, and they all measure temperature and humidity as well.
No VOCs on that.
Okay, so no VOCs on that one, but that's helpful indoors because then you can also see, and that's a true CO2 sensor, so you can see if you're adequately ventilating, and then that has a nice feature that has a visual display, so you can, if you don't want to have to pull out your smartphone to see what you're doing, you just look across the room and you can just kind of glance at it and see where you are. And that one is linked up with the local air. They link up with the local air monitoring stations, like the EPA air monitoring stations. So it tells you what is being measured with a regulatory monitor close to you, okay, which might not be exactly what's at your house, but at least it's something that's in your area, and then tells you what's inside. So there's some others as well. There's a lot of movement, so a lot of these companies are developing new products. I know that Foobot's coming out they're going to come out with a new product sometime soon. Yeah. Their old product did pretty well for particulate matter when we tested it as well. AirBeam was another one that did pretty well when we tested it previously. Again, lots of new products coming out. There were a couple that we tested that didn't do well, have new products coming out that we haven't tested yet, so I won't mention those names until we test them. But for $200 to $300, you can buy something which will give you some indication, at least of particulate matter, temperature, humidity, and if it has a true CO2 sensor, you can get some sense of ventilation. If you're a person who loves numbers and data and seeing what's going on, then I recommend them.
Yeah, I like them. Yeah. I think the ultimate value for the average homeowner is going to be the story behind the data, which is, oh wow, when I fry this fish, I see that my air quality changes, and when I run the rain to it, I see that it changes again. The story.
Yeah, my colleague and other good friend Lou Harriman. He bought one of these things, and he wanted to demonstrate to his partner how it was his wife, I think, how the cooking really does generate pollutants, and using the range here was beneficial. I don't know if he actually needed to demonstrate that, but he's an engineer, and he really loved to be able to see that, right? Yeah. He was a little bit more dismayed though that they had their old model had the CO2 equivalents, and he's like, okay, I don't think this is quite right. It's not really CO2, and they don't say it's CO2; they say it's CO2 equivalent. So, so seeing it it helps you create the story.
Yeah, absolutely. Right? All right, that's all the questions I had. I was going to ask you, what else, your current research, what are you tracking? But I think, in the interest of time, unless there's something fascinating you want to share briefly.
Absolutely. There's definitely something I want to share, which is that we are, one of the big questions is what's the indoor air quality in new homes, and whether any of these high-performance home programs make a big difference. Now, we know, based on lots of research, that the elements that we're putting into these high-performance homes work, okay? But what we don't know is the experience of the people who are in those homes. Mm-hmm. And we take the experience of the occupants very seriously, right? So perceptions matter. So we put together a survey. It's unfortunately rather long, but it asks for a lot of really meaningful elements of the home and people's experience and what they do in their home too. So the website is iaqsurvey.lbl.gov. IAQ survey, you'll do it on your website .lbl.gov. And if your home was built since 2010, please go and check out the survey. Tell your friends about it. And we're hoping that in a couple of years, we're hoping that within a year or so we'll have some good data where we can see whether these homes that are built with the high-performance features actually produce air quality that people perceive as better, in addition to it having lower concentrations of pollutants.
Oh, I like that idea. And how much is meaningful data? How many survey respondents do you think?
We'll see what we get. There's another. You asked what else we're doing is new. The Building America program, we get a lot of funding from Building America. It's a great program. It's an industry-oriented program, so it's designed to help the industry build better houses, to provide the information that is needed for the industry to do that. They're interested in the same question of saying, okay, what is the indoor air quality currently in new homes, looking both at homes that are built with mechanical ventilation and homes that are not. So the study is happening in 3 parts of the country, actually 4 parts of the country. So the Southeast U.S., the 2 climate zones of the Southeast. It's happening in Oregon, Colorado, and it will be happening starting soon in Illinois. So around the country. And the idea is to look at ventilation equipment use and indoor air quality perceptions, so that people in that study are doing the same survey, and then we're measuring a bunch of pollutants. So it's measure pollutant levels, equipment use, and satisfaction in these new homes that are with and without mechanical ventilation. And very cool, we're doing, as part of that, 2 other things we're doing. Some of those homes we're going to measure with and without the ventilation operating. So we're going to see what that does for the pollutant levels.
Right.
And the EPA, with some co-funding from EPA, we're also looking at the effectiveness of radon-resistant new construction. So that's part of the EPA Indoor Air Plus program. The idea being you set the home up in especially in radon zone 1 areas, so areas where you tend to have high radon. When you build a house, okay, you set it up for active radon protection, but you don't put the fan in. This is a passive system. Preliminary research or prior research has shown these things to be pretty effective, but we want to try to nail that down a little bit better, and also determine how much benefit you get from that passive vent. Awesome. So there's a radon element to it. There's the with and without ventilation, baseline indoor air quality in these new homes. And then that follows a study we did in California recently, where we looked at 70 new homes that were built with the code-compliant mechanical ventilation. And in those homes, just to highlight, we found that the homes all had compliant systems in them for general ventilation. Most of them had compliant kitchen ventilation, although some of the microwaves didn't move as much air as they're supposed to. Right. And we found these homes were built with the low formaldehyde materials. We found generally lower pollutant levels than we saw in California homes 10 years ago, and much lower formaldehyde levels. And even the nitrogen dioxide, these are homes with gas, even the nitrogen dioxide levels were lower than we'd seen it in previous studies with gas homes. So these homes built with the code-compliant ventilation, when people use them, really works well.
That's awesome.
All righty. Thank you, Brett. That was great. What a feast of ideas. Did you catch the cooking pun? And thank you all for listening, and we'll talk to you next time.